In this video, we are going to do another trig sub example. So we are trying to do the integral from 0 to 1 over 5 of this fractional function. So there's actually a couple ways to do this one, but because we're practicing trig sub, let's try to do it with that. So the indicator that we might try a trig sub is that this denominator is actually a square root in disguise. It's the square root of 1 plus 25x squared, and then that whole thing getting cubed. That's how I can rewrite that fractional power. And we've seen before in our last video on trig sub that terms like this lend well to a trig sub. So when I'm looking at my Pythagorean theorem, a squared plus b squared equals c squared, if we isolate for a leg like a, we get that a equals c squared minus b squared, that whole thing getting square rooted. But I don't see a minus in my square root. Both terms are added, and we get stuff like that if you isolate for the hypotenuse, because c is going to be equal to square root of a squared plus b squared. So that indicates that now, when we set up our right triangle, let's make our side be the hypotenuse. So we're going to make the hypotenuse be that square root term that we see. Square root of 1 plus 25x squared. So to find the other sides, let's set up our Pythagorean theorem. That'll give me, a mystery leg squared plus another mystery leg getting squared equals a hypotenuse getting squared. So that square root of 1 plus 25x squared, that whole thing getting squared. Okay, and if I square that hypotenuse, it gets rid of the root, and I get 1 plus 25x squared. And at this point, I want to pause the video for a quick 30 seconds. To see, can you figure out what goes in these two parentheses so that it works out to this? So pause it for 30 seconds. In 3, 2, 1, pause it. All right, so hopefully you paused it to try it. So it turns out that what works is if you let one of these parentheses be 1 and the other one be 5x. So I'm going to make those be the legs of the right triangle. It doesn't really matter which one I put where. So maybe I'll make 5x be this one and 1 be that one. And now I label one of the angles in the triangle as theta. And again, it doesn't really matter which one. We can make it work either way. But maybe I'll make theta be this one at the bottom. Okay. So now the next step is we want to create trig expressions for the things that I see in my integral. So the thing on the denominator has this square root term. So let's set up a trig function that involves that square root term. There's multiple possible options. Like I can do something that involves the hypotenuse and the adjacent side. I can do something that involves the hypotenuse and the opposite side. Typically, whichever one we're focusing on, so right now I'm focusing on this hypotenuse, the other side that I pick with it, we usually like it to be a constant, which in this case is 1. If you do something that also involves the 5x, you might introduce an extra variable, which might make it more complicated to work with. So, okay, what trig function can I use that involves these two? So I can either do cosine or I can do secant. Maybe let me do secant just so that this square root term ends up on the numerator. So secant is that hypotenuse 1 plus 25x squared over 1 over the adjacent, which is just the square root of 1 plus 25x squared. Okay, I'm going to highlight this. Because for this denominator portion, we are going to be able to plug in this secant term. On the numerator, though, I see this x cubed term. So I see x showing up as this opposite side. What trig function can I involve with this one? Well, again, I probably want to involve this in the constant side. So for that, maybe I can do tangent. So tangent of theta is opposite over adjacent, so 5x over 1, which is just 5x. Nice. So to be able to plug in for this x that I see here, we would need to isolate x. Okay, so if I isolate x, I divide by 5, and I'll get that 1/5 tangent of theta is equal to x. So let's highlight this as well. So this x is just equal to 1/5 tangent theta. The other thing that we'll need to plug in for is this dx. And to get dx, we pick one of these substitutions and we do the derivative of it. typically whichever one looks simpler to do the derivative of. And it looks simpler to do the derivative of x than to do the derivative of this square root term. Okay, so let's do that derivative. So let's take the derivative of this. And if we do that, on the left-hand side, I get 1/5 times secant squared theta. I pop out a d theta. And derivative of x is just 1. And then I get a dx. Nice. Okay, so dx is just 1/5 secant squared theta d theta. So I get to plug that in for dx. Because I have a definite integral, we also need to convert these are right now x values, into theta values. So I can plug that into either one of these substitutions. So maybe I'll plug it into this one. It just looks a little simpler. So if we do that, one of the x values is 0. One of them is 1/5. So if I plug in 0 for this x, we are going to get that tangent of theta. If I rearrange this, if I multiply the 5, I get 5 times 0, which is 0. And for the bottom one, I'll get tangent of theta equals, there'll be a 1/5 here. I can multiply the 5 over, and it'll give me tangent of theta equals 1. And we saw in the previous video that, technically there's infinitely many angles that work for both of these. But when we do this trig sub, we have to restrict what the angle can be. So for tangent, the convention is to restrict it from negative pi/2 to positive pi/2. That's the portion of the graph where it's going to pass the horizontal line test. And the convention is to pick this in this middle region of the graph. Okay, so if we do that, when is tangent equal to 0? Well, that's when theta equals 0. When is tangent 1? Well, it's when theta is pi/4. Okay, so subbing in, that bottom limit, the 0, just became 0. The 1/5 became a pi/4. And now in my fraction, let's see, we have 5 multiplied by x cubed. And the x, well, the x was that 1/5 tangent of theta. The denominator is where we were plugging for that square root term. But that whole square root term was getting cubed. And the square root term was just secant of theta. So that's getting cubed. And then finally, we got that dx at the end. And dx, we said, was just 1/5 times secant squared theta d theta. Okay, so we've converted our integral to thetas. So this can get simplified a little bit. Like I can cancel this 5 on the denominator with this 5 up in the numerator. I still have this 1/5 getting cubed, which I can pull to the front of the whole integral as 1 over 125. I got my integral from 0 to pi/4. And this will leave me with, let's see, we got tangent cubed on the numerator. And then on the bottom, I have secant cubed. On the numerator, I have secant squared. So I can cancel 2 of the secants to be left with secant squared theta, d theta. Okay, so it's looking a bit simpler. And I have to do this antiderivative. One of the ways I can try to handle this is try to convert all the tangents and secants into like sines and cosines. So tangent is sine over cosine. So I'll get sine cubed over cosine cubed. That whole thing divided by secant squared. Secant is 1 over cosine, so I'll get 1 squared, which is 1, over cosine squared. And when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So this whole thing will get multiplied by cosine squared over 1, which will cancel 2 of these cosines. So overall, that's leaving me with 1 over 125 in front, times the integral from 0 to pi/4. And we have sine cubed theta all over. And I'm realizing I made one error earlier. So the one error, let me go back and fix that, which was I wrote secant squared on the bottom, but it should just be secant because there were 3 secants here, 2 secants there. So let us go back and fix that. This one should have just been secant, not secant squared. So I'm changing that secant squared to secant, which means this should have just been 1 over cosine. So let's fix that as well. Okay. So now when I simplify this fraction, and when I multiply by the reciprocal, I'll get sine cubed up top over cosine squared on the bottom. And then I still got d theta. Okay, so now we have to do this integral. So I noticed that with this, it would work so well for a u sub by letting u be cosine if the numerator was just sine. So one thing I can do to kind of split out a sine is to write the numerator as sine squared theta times an extra sine theta. And I don't really love the fact that sine squared is there, so we can do a trig identity on that to write that as 1 minus cosine squared, and then times that other sine. And now we can do a u sub on this. So now let's let u be cosine theta. So then du would be negative sine theta d theta. Okay, so now we're going to be able to sub in for this. But because I have a definite integral, I got to convert these theta values to be in terms of u. So I have theta being equal to 0 and pi over 4. So to convert them, we plug into our u sub. So cosine of 0 is 1. And if I plug in pi over 4, cosine of pi over 4 is root 2 over 2. Nice. Okay. So now I have 1 over 125. That 0 on the bottom converted to a 1. Pi over 4 converted to root 2 over 2. And the whole numerator became this, right? 1 minus cosine squared times sine theta. So plugging in for the cosine, I get 1 minus u squared. Okay. And then I still have that sine theta. All over the cosine squared on the bottom, which becomes u squared. And if I isolate for d theta here, well, d theta is du over negative sine theta. Okay. So I can cancel a sine on the top and the bottom. That leaves me with 1 up here and a negative 1 down there. I can move the negative out in front. In fact, one of the things I'm realizing is, wait, I can change the sign entirely if I were to flip these limits of integration. So if I were to flip them, I get 1 over 125. Flip them to get root 2 over 2 on the bottom and 1 up top. And that gets rid of that negative 1. Okay. And now in my integral, we got 1 minus u squared over u squared du. Okay. So we are almost at a point where we can do this. I just have to simplify this fraction. So I can split this up as 1 over u squared minus u squared over u squared. And that u squared over u squared just becomes 1. So now I'm ready to do the antiderivative. We got 1 over 125. Big old bracket. Antiderivative of this is u to the negative 2. That antiderivative would be negative 1 over u, doing my reverse power rule. Antiderivative 1 is just u. Close the bracket. And then I got to plug in my limits of integration, the root 2 over 2 and the 1. So I got to plug these in for the u and then subtract. So when I do that, I will have to combine some like terms. I'm going to trust that we can do that. I'm going to skip one of that steps. I'm just going to skip the step when we plug in and just tell us what we end up getting. We will end up getting 1 over 125, big old bracket. And what we end up getting is 2 over root 2 plus root 2 over 2 minus 2. So we will end up with this. And that's our answer. Okay, so this was a longer problem. We needed to do a trig sub, and then later we got to something where we needed a further u sub to handle it. So definitely multiple steps in one here. I mentioned at the beginning that there's more than one way to do the problem. Another way that we could have done this from the beginning was to do a simple u sub. So sometimes we won't always need a trig sub to do a question, although even if we could do it. It turns out if you let u be equal to the stuff that's inside of this power, that can end up working. So I'd encourage you to try that as a practice problem.